The Golden Gate Bridge is quietly rotting in the ocean air. In 2021, crews burned through 2,590 gallons of paint and 720,000 pounds of blasting sand just to keep rust from spreading. That's not painting, that's steel surgery. And here's the part nobody wants to say out loud. America doesn't finish repairs like this. It stretches them, patches what's urgent, phases what's expensive, and pushes the full reset into the future. And the brutal part is this: you never finish the job. Some sections need repainting every 10 to 20 years depending on exposure. So the bridge isn't aging. It's on a countdown that resets forever. Now the money, because this bridge runs on cash as much as steel. The bridge division's operating spend was $108.4 million in fiscal years 2024-25, with $119.6 million proposed for fiscal years 2025-26. So when people say, just fix it properly, they don't realize what that means. You'd have to slow the bridge down to save it, and the Bay can't afford that. On paper, it's an American icon. In reality, it's a working steel machine sitting in a corrosion lab, and rust is the slow killer. And earthquakes? They're the nightmare scenario, not because they cause rust, but because that's the day every hidden weak spot gets tested all at once. Today we're going under the paint, into the seams and joints to see what's actually happening. Joseph B. Strauss drove the project as chief engineer, but it wasn't a one-man bridge. Leon Moisseiff pushed the final suspension concept, Charles Alton Ellis did much of the core structural engineering, and Irving Morrow shaped the Art Deco look and chose international orange. They built it because ferries across the Golden Gate Strait were a bottleneck, and the Bay needed a reliable link between San Francisco and Marin. And in the Great Depression, it doubled as a jobs engine. Construction began in 1933, when work mattered as much as the bridge. Construction officially started January 5, 1933. It opened with huge celebrations on May 27, 1937, when people crossed on foot before cars were allowed. Public reaction wasn't universally proud, it was polarizing. Strauss had to beat heavy opposition, ferry operators, conservationists, even engineers, and the financing turned into a bitter political battle, including a bond vote in November 1930. And the workers? Many knew they weren't building just another bridge. They believed they were building one of the greatest engineering works of the era. They built it in the worst possible place for steel, and the ocean has spent the next 90 years trying to take it back. The Golden Gate is basically an outdoor corrosion lab. Fog wets the steel, salt gets deposited, wind drives moisture into seams and crevices. When coatings peel or crack, the bridge's own exhibit explains the chain reaction. Steel gets exposed to oxygen and water, corrosion starts, and maintenance must remove rust down to bare steel before reapplying primer and top coats. And corrosion doesn't hit the bridge evenly. The district's exhibit states that different areas of the bridge are repainted about every 10 to 20 years, depending on exposure. That's a huge clue. The bridge isn't one surface. It's thousands of microenvironments, and some of them are always losing the fight faster than the rest. Now earthquakes, one clean, honest line, because this is still a rust story. Earthquakes don't cause rust, but they spend your remaining margin in seconds. If corrosion has been quietly thinning a connection detail or undermining a protected interface, a major quake is when that weakness stops being maintenance and becomes damage. That's why the bridge is also in a long-running seismic retrofit program, and why planning documents talk explicitly about cost models and budgets for seismic work. Rust is the slow threat. Quakes are the stress test. To see where that stress test hits hardest, you have to understand how this bridge is built. The Golden Gate Bridge is a suspension bridge, which means it's not one rigid object. It's a tension system. Anchorages hold cable forces, towers shape the cable geometry, main cables carry tension, suspenders transfer load down to the roadway structure, and the roadway system controls how the deck behaves under wind and traffic. That design choice is why the bridge became an icon, because it could span a difficult strait with a structure that's strong without being a solid wall of steel. But here's the key for rust. Suspension bridges have an enormous number of interfaces. Every interface is a place where coatings are stressed and where moisture can sit, overlaps, seams, edges, and connection geometries. And because the bridge is built to move, those interfaces don't sit still. They experience micro-movement from wind, daily temperature swings, and traffic cycles. Over years and decades, that motion is a quiet amplifier. It increases the chance that coatings fail at the exact locations you least want exposed steel. Now the earthquake. A major quake punishes the bridge at its critical details and connections. If rust has reduced the margin at those details, the bridge becomes less forgiving. This is exactly why the final phase of the seismic retrofit is framed around keeping the bridge serviceable after a big event, and why the total estimate discussed publicly is on the order of $1.8 billion. But this project, your project, is about rust. So we pivot back to the real day-to-day truth, where corrosion begins. The bridge's genius is controlled flexibility. A suspension bridge survives wind and load by distributing forces and allowing movement within a designed range. That's the physics that makes it work. But the same movement that keeps the bridge stable under dynamic loads also creates a long-term maintenance reality. Coatings fail first where geometry and motion concentrate stress. Edges are thinner coated than flat faces. Seams and overlaps trap moisture. Joints experience tiny slip and vibration. Underdeck steel dries slower. All of that means corrosion doesn't announce itself with a dramatic crack. It announces itself by winning the small battles you don't see. This is why the paint myth exists. People look at the bridge and assume it must be repainted end to end on a strict schedule. The district itself addresses that misconception. Some people say it's painted once every 7 years, others say end to end each year, but the truth is the bridge is painted continuously as an ongoing maintenance task. That line isn't a fun fact, it's a warning. The bridge survives by staying ahead of coating failure. When the cycle slips, corrosion doesn't pause, it compounds. So what does a head actually look like on steel? It looks like target zones, places where rust starts first. Rust doesn't start on the postcard angle, it starts at the details. The district's exhibit puts it in simple cause and effect language. When protective paint peels or cracks, steel is exposed and corrosion initiates. Maintenance requires removing rust down to bare steel before primer and top coats go back on. That's the real rule. Paint over rust and you're not fixing anything, you're just hiding a process that continues underneath. So the high-risk zones are predictable, where water lingers longer, where salt deposits accumulate, where steel geometry creates crevices, where access is hardest, so the work is slower and more expensive. This is where the 10 to 20 years interval matters again. Some bridge areas, by exposure and geometry, will lose coating faster, meaning they demand more frequent intervention. That's why you can see a perfect finish in one place and a rough patch in another without it meaning the bridge is neglected. It usually means triage. Resources are being aimed at the places that either 1. Corrode fastest, or 2. Matter most structurally. And that takes us to the part everyone asks for, the cost. Because the bridge doesn't just run on steel and chemistry, it runs on money. When people ask, how much does it cost to paint the Golden Gate Bridge? They usually mean the paint. That's not where the bill is. SF Gate reports that in recent years the annual budget for paint, including the sand used to blast off old coating, has been about $300,000 per year. That's materials. But the actual cost driver is everything needed to safely apply those materials to a steel structure suspended over water and wind under environmental restrictions, with traffic still moving. SF Gate describes the process. Engineers identify areas, then iron workers set up 70 by 70 foot containments to hold in blasted sand and paint so that nothing but rainwater can fall off the bridge. That containment work is labor, equipment, and time. And it exists because you can't treat old coatings and corrosion like a backyard project. Now here's another hard number you can use to show scale without guessing. The district publishes annual traffic crossings. For example, total traffic is listed as 40,003,340 for fiscal year 2019 and 33,469,296 for fiscal year 2024. That matters because it answers the question, why not close it and repaint everything perfectly? The bridge isn't just an icon, it's a moving piece of regional infrastructure with tens of millions of crossings. Every closure has consequences. Every maintenance choice is constrained by the fact that the bridge has to keep doing its job. And while your video is rust first, the seismic retrofit costs are part of the broader real bill story. Public reporting puts the total seismic retrofit finish estimate around $1.8 billion, with the next phase beginning in January 2026 and involving major strengthening and energy dissipation devices. So even if the audience came for rust, they leave with the real insight. This bridge is a permanent maintenance machine, and the price of survival is not one number, it's an ongoing portfolio of work. Which brings us to the title question. If you want a single year, it'll last until 2080, you won't get an honest answer from any competent engineer, because the bridge doesn't have an expiry date the way a warranty does. It has a maintenance equation. Here's what we can say, cleanly and factually, without hype. The district says painting is continuous because it protects steel from salt-driven corrosion. The district's exhibit explains that once protective paint fails, corrosion initiates, and proper maintenance requires removing rust down to bare steel before rebuilding primer and top coats. The exhibit also states that different areas are repainted about every 10 to 20 years, depending on exposure. And a documented year of work used 2,590 gallons of paint and 720,000 pounds of blasting sand, which proves the fight is constant and industrial in scale. So the survival answer is this. The Golden Gate Bridge can keep surviving as long as corrosion is kept from becoming structural, meaning the maintenance cycle stays ahead of corrosion spread, especially at high-consequence details, edges, and interfaces. If the cycle slips long enough, the job escalates. You move from coatings to steel replacement and rehabilitation. That's when maintenance turns into rebuild. And earthquakes are the final, brutal punctuation mark on that reality. They don't create rust, but they reveal what rust has already weakened, fast. That's the truth under the paint. Not a romantic story, not a collapse story, a corrosion story, measured in containment boxes, blasting media, primer systems, and whether the bridge's maintenance machine keeps running long enough to outlast the ocean.